Right. Right. And we got the record on. Before we do this, I'm going to do two things. First, I'm going to prove that this is a misspelling of Monsieur de Laplace. Boom, boom, boom. I think I have it on my desktop actually. So here we go. This is the original, or at least a copy of the original, you know, Triet Elementary de Guimet from, what is that, L is 1, 10, 10, 10. So, oh, no, 50, 50, 89. It's 89. Yeah. 7, 1, 7, 2 centuries plus the, I guess D is 500. Millennium, 1000. Boom. So yeah, 1500 plus 200, 1700, 50, 80, 1 minus 10, 9. 1789. Anyways, de la place. Monsieur de la place est moi. Who is moi? Who is moi? Monsieur de la place is moi. Is tu. No, no hablo français. Miss Lucie. So just so you know, this is, I know everywhere says la plus. Everyone. It's just another thing that everyone has wrong. And people want to argue like there's this giant scientific anti-intellectual movement, but you guys, there's so many things that are wrong. We got to fix this first, and then we can convince people that science works because fixing this is part of what science does. So, I'm listening to myself. I'm on the delay, but it was a good rant. I'll listen to myself. Let's see if we could find, because this has section 1 and section 4. But let's see if we can find memoirs. Eat. Hier, Simone de la Place. My spelling's not great ever, so let's see. Is this an actual thing? Article has no line. It's just a citation. Google Books. Maybe the full thing. How do I? Okay. How do I read it? Why are we recommending things without recommendation? All right, Google Books. Okay. That's why. Okay. Yeah, guinea pigs. This one's kind of like the one that I had. I'm gonna have to learn how to read French just to learn how to read this stuff. Ay, 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 ay. You gotta do what you gotta do. Hmm. I hate it when it takes control. Um, I don't need to purchase a subscription. I just need information. Where is it though? I see it. I see it. I see it. That is kind of cool. Hmm. I need a new document. Um, I don't see anything. I okay. Oklahoma. Sure. Interesting. We're in a loop. Where do I get the book? This is like the only where in the world to find it. Hmm. Signed copy. I wish they would try. Signed in. I'm not a student. Sucks. Gatekeepers. I wish I speak Arabic. No. All right. I'm missing sections 2 and 3 from this reading. It's over. Just gonna read sections 2 and 4. Oh, great. Oh, I got a lot of stuff. You guys don't even know. Here, while I'm doing this, I'm going back to music. Pierre Simon de Laplace. Huh. I guess it's kind of fun. I could talk out loud. I could talk to myself because I'm just live now. Oh. Hmm. All right. Um, mm, I really don't feel like I got time to do this, but once I do it once, I'll never have to do it again, and I can always come back to it for the YouTube version to re-listen to it. So it's going to be a good investment. 14 pages might take me 2 hours to read, but might as well. All right. All right. Go live. Okay. I don't know if I'm going to be able to do this with the mic in. All right. So I'm just going to freestyle this. This is a reading of the Memoir on Heat, read to the Royal Academy of Sciences, 28th of June, 1783, by Antoine Lavoisier and Pierre-Simon de Laplace. This memoir is the result of experiments on heat which we have made together, Monsieur de Laplace and I, in course of last winter. The moderate cold of that season did not allow us to make more of them. We had first proposed to wait before publishing anything on this subject until a colder winter can enable us to repeat them with all possible care, and to make more of them, but we decided to make this work public, although it is very imperfect, because the method that we have used may be of some use in that theory of heat, and because its precision and wide applicability could lead to its adoption by other scientists who, situated in the north of Europe, have winters very favorable for this kind of experiment. We will divide this memoir into 4 sections. In the first, we will describe a new way of measuring heat, We will present in the second the results of the chief experiments which we have made by this means. In the third, we will examine the conclusions that follow from these experiments. Finally, in the fourth section, we will treat combustion and respiration. Section 1. Description of a new means of measuring heat. Whatever may be the cause that produces the sensation of heat, it is able to increase and decrease, and, from this point of view, it can be treated quantitatively. It does not seem that it occurred to the ancestors to measure these relative values, and only in the past century have men conceived of ways of doing so, starting with the general observation that heat of greater or less intensity perceptibly varies the volume of a body, especially that of fluids. Men built instruments capable of measuring changes in volume. Many natural scientists of this century have greatly improved these instruments, either by determining accurately certain fixed points of temperature, such as the freezing point and the boiling point of water at a given atmospheric pressure, or by searching for the fluid whose changes in volume would come nearest to being proportional to the variations of temperature, so that there remains nothing more to wish for relative to its measurement, except a sure means of determining the extreme degrees. By the knowledge of the laws that heat follows when it is diffused through bodies, it is far from that degree of perfection necessary for analyzing the problems relating to the communication of heat and its effects in a system of unequally heated bodies, especially when their mixture breaks them down and forms new compounds. A great number of interesting experiments have been made, which show that in change from the solid to the fluid state and from the fluid to the vapor state, a large quantity of heat is absorbed, either because it is combined in this transformation or because the capacity of the substance to contain it increases. In addition, it has been observed that at the same temperature, the same volume of different substances does not contain equal amount of heat, and that among them there are, in this respect, differences, independent of their respective densities. Even their relative heat capacities of various substances have been determined, and since even the coldest bodies on the Earth's surface are not entirely without heat, some have tried to discover the relations of absolute heat to its changes as shown by readings of a thermometer. But all these estimates, although very ingenious, are based on hypotheses which must be confirmed by a large number of experiments. Before proceeding further, it is essential to establish precisely what we mean by the terms of free heat, heat capacity, or specific heat of bodies. Scientists are divided about the nature of heat. A number of them think that it is a fluid diffused throughout nature, and by which bodies are more or less permeated according to their temperature and to their special faculty for retaining it. It can combine with them. In that state, it ceases to act on the thermometer and to pass from one body to another. It is only in the free state when it can reach equilibrium among bodies, and it constitutes what we call that. Restart. It is only in the free state, when it can reach equilibrium among bodies, that it constitutes what we call free heat. Other scientists think that heat is only the result of the imperceptible motions of the constituent particles of matter. We know that even the most dense bodies are filled with a great number of pores or tiny empty spaces, whose volume can considerably exceed that of the matter that they enclose. These empty spaces allow the imperceptible particles to oscillate freely in all directions, and it is natural to think that these particles are in a constant agitation, which, if it increases to a certain point, can break them apart and so decompose the bodies. This is the internal motion, according to these scientists, we are speaking of that constitutes heat. To develop this hypothesis, we shall point out that in all motions where there is no abrupt change, there exists a general law which the mathematicians have called the principle of the conservation of vis viva. This law states that in a system of bodies that act on one another in any manner whatsoever, the vis viva is to say the sum of the products of each mass by the square of the velocity is constant. The bodies are acted upon by accelerative forces. The vis viva equals what it was at the onset of the motion plus the sum of the masses multiplied by the squares of the velocities due to the action of the accelerating forces. In the hypothesis we are considering, heat is the vis viva resulting from the imperceptible motions of constituent particles of the body. It is the sum of the products of the mass of each particle by the square of its velocity. If you put in contact two bodies whose temperatures are different, the quantities of motion that they communicate to each other will at first be unequal. The vis viva of the colder will increase by the same amount that of the other decreases. And this increase will take place until the quantities of motion communicated from one body to the other are equal. In this state, the temperatures of the bodies will have become equal. This manner of viewing heat easily explains why the direct impact of the sun's rays is indetectable, whereas they still produce a great heat. Their impulse is the product of their mass by their velocity. Now, although their velocity is excessively great, their mass is so small that the product is almost nil, while, on the other hand, their vis viva being the product of mass by the square of the velocity, the heat that it represents is very much greater than that of their direct impact. This impact of the white body, which reflects light abundantly, is greater than on the black body, and yet the solar rays communicate less heat to the former because these rays are being reflected, carrying away their vis viva, whereas they communicated to the black body which absorbs them. We shall not decide between these two hypotheses. Several phenomena seem to favor the latter, such as, for example, heat produced by the friction of two solid bodies. But there are other phenomena that are explained more simply by the first hypothesis. Perhaps both occur simultaneously, whatever may be the case. Since only these two hypotheses about the nature of heat can be devised, we should accept the principles common to both. Now, whichever one we follow, in a simple mixture of bodies, the quantity of free heat remains always the same. This is evident if the heat is a fluid that tends to reach equilibrium and also if it is only the vis viva which results from the internal motion of matter, where the principle in question follows from the conservation of vis vivae. The conservation of free heat in the simple mixture of bodies is thus independent of any hypothesis about the nature of heat. It has generally been accepted by scientists that we shall adopt it in the following investigations. If heat is a fluid, it is possible that during the combination of various substances, it combines with them or is evolved from them. Thus, nothing indicates a priori that the free heat is the same before and after the combination. Nothing, moreover, suggests that in the hypothesis that heat is only the vis viva of the particles of body, in the substances that combine together, acting on one another by virtue of their mutual affinities, their particles are subjected to the action of attractive force that can alter the amount of their vis viva and consequently the amount of heat. But one should accept the following principle as being common to the two hypotheses. If in any combination or change of state there is a decrease in free heat, the heat will reappear completely whenever the substance returns to their original state, and conversely, if in the combination or in the change of state there is an increase in free heat, this new heat will disappear on the return of the substance to their original state. This principle, moreover, is confirmed by experiment, and in what follows the denotion of saltpeter will furnish us with visible proof. We can generalize it further and extend it to all phenomena of heat in the following way. All changes in heat, whether real or apparent, suffered by a system of bodies during a change of state reoccur in the opposite sense when the system returns to its original state. Thus the changes of ice into water and of water into vapor cause the thermometer to show the disappearance of a very considerable amount of heat which reappears in the change of water into ice and in the condensing the vapors. In general, you can turn the first hypothesis into the second by substituting the words free heat, combined heat, and evolved heat for the words vis viva, loss of vis viva, and increase in vis viva. Because of our ignorance as to the nature of heat, we can only observe carefully its effects, the chief of which consists in expanding bodies, turning them into fluids, and converting them into vapors. Among these effects, we must choose one that is easy to measure and that is proportional to its cause. This effect will represent the heat just as in dynamics we represent force by the product of mass and velocity, although we are ignorant of the nature of the particular modification in virtue of which a body reaches successively different points in space. The effect through which we commonly measure heat is the expansion of fluids, and chiefly that of mercury. The expansion of this fluid, according to the interesting experiments of M. Deluc, is very nearly proportional to the heat. Throughout the whole interval between the freezing point of ice and the boiling point of water, it can obey another law at more extreme degrees of temperature. We shall indicate in what follows another effect of heat, which is always proportional to it, whatever its intensity. We shall use a mercury thermometer divided into 80 equal parts, from the temperature of melting ice to that of boiling, at an atmospheric pressure of 28 inches of mercury. Each division marks a degree, and the origin of the degrees, or the zero of the thermometer, is the melting point of ice, and so that the degrees below should be taken as negative. We shall imagine the scale of this thermometer extended indefinitely both below zero and above the boiling point of water, and divided in proportion to the heat. These divisions, which are nearly equal from 0 to 80 degrees, can be marked unequal in the remote portions of the scale, but in any case each degree will always measure a constant amount of heat. If one imagines two bodies of equal mass brought to the same temperature, the quantity of heat necessary to raise the temperature by 1 degree may not be the same for the two bodies, and if one takes as unity the amount of heat which can raise the temperature of a pound of plain water by 1 degree, it is easy to see that all other amounts of heat of different bodies can be expressed in terms of that unit. In what follows, we shall mean by heat capacities or specific heats the relative quantities of heat necessary to rise the temperature of equal masses to the same number of degrees. These ratios can vary at different temperatures. If, for example, the quantities of these ratios can vary at different temperatures. If, for example, the quantities of heat necessary, the H is cut off, of heat necessary to raise a pound of iron and a pound of mercury from 0 to 1 degree are in the ratio of 3 to 1. So the amounts that must be used to raise the same substance from 200 to 201 degrees can be in a larger or smaller ratio. One can suppose that these ratios to be nearly constant from 0 to 80 degrees. At least experiment in this range has not led us to note any sensible differences. or difference. It is within this interval that we shall determine the specific heats of various substances. To determine these quantities, we use the following method. Let's consider a pound of mercury at 0 degrees and a pound of water at 34 degrees. On mixing them together, the heat of the water will pass into the mercury, and after a few moments, the mixture will take uniform temperature. Let's suppose that is 33 degrees, and that in general, in a mixture of several substances which do not react chemically with one another, the quantity of heat always remains the same. According to these assumptions, the amount of heat lost by the water would have raised the temperature of the mercury 33 degrees. Whence it follows that to raise the mercury to a given temperature, there is only required the 33rd part of heat necessarily to raise water to the same temperature, which is tantamount to saying that the specific heat of mercury is 33 times less than that of water. From this we can infer a general and very simple rule for determining by the method of mixtures the specific heat of bodies. Or if we call the mass of the warmer body M, expressed in fractions of the pound taken as unity A, the reading of the thermometer indicating its temperature Q, the heat necessary to raise the temperature 1 pound of this substance 1 degree. If one designates by M prime, A prime, and Q prime the same quantities for the cooler body, and if finally one denotes by B the temperature of the mixture when it has become uniform, it is evident that the heat lost by the body M is proportional to the mass M to the temperature of degrees A minus B, which the temperature has been decreased multiplied by Q, the quantity of heat which can raise the temperature of this substance 1 degree. Thus, the expression for the quantity of heat loss will be M Q dot A minus B. I think it's M times Q, but is it the dot product of A minus B or just M times Q times A minus B? No, it's just, I think it's showing the multiplication separate from the parentheses. I think that's just maybe a stylistic type of writing. Sorry for the meta. So thus the expression for this quantity of heat loss will be M times Q times times parentheses A minus B end parentheses. I don't know how you say that over mic. For the same reason, the quantity of heat acquired for the body M prime is proportional to the mass M prime and to the number of degrees B minus A prime by which the temperature was increased, multiplied by its own quantity Q prime, which gives M prime times Q prime times parentheses B minus A prime end parentheses for this quantity of heat. But since we propose that after the mixture the quantity of heat is the same as before, we must equate the heat loss by the body M to the heat gained by the body M prime. Once we obtain equation 1 is equal to equation 2, M times Q times A minus B is equal to M prime times Q times B minus A. This equation does not give the value of Q or Q prime, but expresses their ratio as Q over Q prime is equal to M prime times B minus A prime over M times A minus B. And so I'm hesitating there. It doesn't have the Q prime on the bottom, but by the normal product rule, it's Q over Q prime. So in this manner, we have the ratio of the specific heat of the two bodies M and M prime, so that if one compares the different substances in nature with one and the same substance, for example with ordinary water, one will be able by this means to determine the specific heats of these substances in terms of the specific heat of the substance to which we relate them. This method in practice is subject to a large number of disadvantages which can cause appreciable errors in the results. The mixing of substances with very different specific gravities, such as water and mercury, is difficult to carry out so as to be certain as all its parts have the same temperature. It is necessary to take into account the heat that is lost to the vessel and to the atmosphere as the mixture reaches a uniform temperature, which requires a delicate computation that is subject to error. But by this process, moreover, we cannot compare directly substances that act chemically upon each other. In this case, we must compare them to a third substance which they do not react. And if no such substance exists, we must compare them with two bodies, and even with a greater number, by which by multiplying the ratios to be determined with respect to each other multiplies the error of the result. Moreover, this method would be almost impossible to use to measure the cold or heat produced by chemical combinations, and it is absolutely inadequate for determining the heat given off in combustion and respiration. Since observing these phenomena is the most interesting part of the theory of heat, we have thought that a method capable of measuring them with precision would be of great use in this theory, since without its aid one could only formulate hypotheses concerning their cause, which would be impossible to confirm by experiment. Because of this, we decided to take up this problem first of all, and we shall now set forth the method we have arrived at and the train of thought that led us to it. If you convey a mass of ice, cooled down to any degree whatever, into an atmosphere whose temperature is above zero, all its parts will be affected by the heat of the atmosphere until their temperature reaches zero. In the last state, the heat of the atmosphere will stop at the surface of the ice without being able to reach the interior. It will serve only to melt a first layer of ice, which will absorb it on turning into water. A thermometer placed in this layer will remain at the same temperature, and only the perceptible effect of the heat will be the transformation of the ice into a fluid. When afterwards the ice receives more heat, a new layer will melt, and thus will absorb all the heat imparted to it. Because of this continued melting of ice, all the interior parts of its mass will arrive successfully at the surface, and it is only here that they will begin to experience again the influence of the heat of the surrounding bodies. Let us now imagine a hollow sphere of ice at 0 degrees placed in an atmosphere whose temperature is above zero, and inside of which we placed a body warmed to a given temperature. It follows from what we have just said that the external heat will not penetrate into the cavity of the sphere, and that the heat of the body will not be lost to the outside, and will stop at the interior surface of the cavity, of which it will continue to melt new layers, until the temperature of this body has reached zero. There is no reason to fear that the melting of the interior of the ice will be due to other causes than the heat lost by the thickness of the ice that separates it from the atmosphere. For the same reason, we can be confident that all the heat of the body, on being dissipated, is stopped by the interior ice and serves only to melt it. So if, when the temperature of the body has reached zero, we carefully collect water enclosed in the cavity of the sphere, its weight will be exactly proportional to the heat that this body will have lost in passing from its original temperature to that of melting ice. For it is clear that double the amount of heat must melt twice as much ice. The quantity of melted ice, therefore, is a very accurate measure of the heat used to produce this effect. Now, nothing is simpler than the measurement of the phenomenon connected with heat. Do you wish, for example, to know the specific heat of a solid body? You will raise its temperature a certain number of degrees, afterward placing it inside of the sphere, which we have just mentioned. You will leave it there until its temperature is reduced to zero. You will collect the water produced by its cooling. This quantity of water divided by the product of the mass of the body of the number of degrees its original temperature was above zero will be proportional to its specific heat. As to fluids, you will enclose them in a vessel whose heat capacities you will be careful to determine, and the procedure will be the same for as solids, except that to obtain the amounts of water due to cooling the fluids, you must subtract the amounts of water collected, those which the vessels will have produced. Do you wish to determine the heat given off in the chemical combustion of different substances? You will bring them all, as well as the vessel which is to contain them, to a given temperature of 0, and you will put their mixture inside the sphere of ice, being careful to keep it there until its temperature reaches 0. The amount of water collected in this experiment will measure the heat given off. To measure the cold produced in certain reactions, as in the solution of salts, you will raise each substance to the same temperature, which we shall designate by m degrees. Afterwards you will mix them in the interior of the sphere, and you will observe the quantity of ice melted by cooling the mixture to 0. Let A be this quantity. To determine the number of degrees by which the temperature of the substances is lowered by their mixture below their original temperature m, you will raise the temperature of this mixture to a certain number of degrees m prime, and you will determine the quantity of ice melted on cooling to 0. Let A prime be this quantity. This granted, since to the quantity A prime of melted ice there corresponds the temperature m prime of the mixture, it is clear that the quantity A prime of melted ice should correspond to temperature equal to A times m prime divided by A prime. This is then the temperature that results from the mixture of substances raised to the temperature of m. Accordingly, on subtracting it from m, you will have parentheses A prime times m prime minus A prime times Accordingly, on subtracting it from m, you will have parentheses A prime times m minus A times m prime, and in parentheses divided by A prime, for the number of degrees of cold produced by the mixture. We know that the bodies in passing from solid to the liquid state absorbs heat, and that in returning from the liquid to the solid state they restore it to the atmosphere and to the surrounding bodies. To determine it, let m be the temperature at which a body begins to melt after being warmed to the temperature m minus n, and then placed in the interior of the sphere on cooling to 0, it will melt a quantity of ice that we shall designate by A. After being warmed to the temperature m plus n prime, it will melt. On cooling, a quantity of ice shall designate by A prime. Finally, when heated to a temperature m plus n double prime, it will melt as it cools in amount of ice we shall call A double prime. This granted, A double prime minus A prime will be the amount of ice that can be melted by the fluid body on cooling from n double prime to n prime degrees. Whence it follows that in cooling by n prime degrees, it will melt a quantity of ice equal to n prime times parentheses A double prime minus A prime, n parentheses all over n double prime minus n prime. Likewise, we will find that the body on cooling m degrees in the solid state will melt the quantity of ice m times A over m minus n, so designating by x the quantity of ice that can be melted by the heat given off in changing from the fluid to the solid state. We will have got the total quantity of ice that should be melted by the body heated to m plus n prime degrees. Translation errors. N prime times open parentheses A double prime minus A prime end parentheses all over n double prime minus n prime plus x, that ratio plus x, plus the ratio of m times A over m minus n. The first term of this expression being due to the heat given off by the body before it passes into the solid state. The second term being the effect of the heat given off during this change of state, and the third term being due to the heat lost by the solid body on being cooled to 0. If we equate the preceding quantity to the quantity of A prime of melted ice, we will have n prime times open parentheses a double prime minus a prime close parentheses all over n double prime minus n prime, that ratio plus x plus the ratio of m times a over m minus n is equal to a prime. Simple. Once we derive x is equal to n double prime, the x is equal to the ratio of n double prime times a prime minus n prime times a double prime all over n double prime minus n prime minus the ratio of m times a over m minus n. For precise results, it is advantageous to make n and n prime very small. Not only will this experiment give the value of x, in addition we will have the specific heats of the body in its two states of solidity and fluidity, since we know the quantities of ice that it can melt in these two states on cooling and give a given number of degrees. To find the heat developed by combustion and respiration is no more difficult. You will burn combustible bodies in the interior of the sphere. You will let animals respire there. But since the renewal of air is indispensable in these two operations, it will be necessary to establish some communications between the interior of the sphere and the atmosphere surrounding it. And so, in the introduction of fresh air, and so that the introduction of fresh air will not cause any perceptible error, it is necessary to perform these experiments at temperature differing only slightly from zero, or at least to lower to this temperature the air you introduce. The investigation of the specific heats of different gases is more difficult because of their low density. If you were content to enclose them in a vessel like the other fluids, the amount of ice melted would be so small the result of the experiment would become extremely unreliable. But if you place in the interior of the sphere a tube bent into a spiral and sent through the tube a stream of some sort of air, then by means of two thermometers placed in the stream, one where it enters the sphere and the other where it leaves, you can measure the number of degrees by which the air is cooled during its transit. And you can cool in this manner a considerable mass of the air and determine with precision its specific heat. This same method may be used to determine the amount of heat given off during the condensation of vapors to different fluids. You see, by the detail which we have described matters, that the preceding method extends to all phenomena in which there is the production or absorption of heat. In these different cases, you can always determine the quantities of heat that are produced or absorbed and relate them to a common unit. For example, to the heat necessary to raise the temperature of a pound of water from 0 to 80 degrees. In this way, you can determine and compare with each other the quantities of heat produced by the combination of oil and vitriol with water, and of the latter with quicklime, and of quicklime with nitric acid, etc., and those given off in the combustion of phosphorus, sulfur, carbon, and pyrophore, etc., in the notion of saltpeter, in the respiration of animals, etc., all of which was impossible by methods known up to now. We have considered a sphere of ice only in order to make better understood the method we have used. It would be very difficult to obtain such spheres, but we have replaced them by means of the following device. In Figure 1 of Plate 1 represents the perspective view of this apparatus. Figure 3 shows the horizontal section, the vertical section. In Plate 2, Figure 1 shows the interior, which is divided into three parts. To make matters clearer, we shall distinguish them in the terms inner space, middle space, and external space. The inner space, FFFF, Figures 1 and 3, Plate 2, is in a basket of iron wire held up by a few supports of the same metal. It is in this space that we place the bodies to be experimented on. The upper part, LM, capital L, capital M, is closed by means of the lid, capital H, capital G, separately shown, Plate 2, Figure 2. It is entirely open above, and the bottom is formed by the lattice of iron wire. The middle space, BB, Figure 1, Plate 2, is intended to hold the ice, which is to surround the interior space and be melted by the heat from the body in the experiment. This ice is surrounded and held in place by a screen m, which under which is a sieve, n, sieve. Each is shown separately, Plate 2, Figures 4 and 5. As the ice is melted by the heat of the body put in the inner space, the water flows through the screen and the sieve. Then it falls along the cone c, d, Plate 2, Figure 1, and the tube x, y, and is collected in the vessel P, placed below the apparatus. K is a stopcock, which means of which you can stop at will the overflow of water from the inner space. Finally, the external space A is intended to hold the ice, which is to block the effect of the heat from the atmosphere and surrounding bodies. The water produced by melting this ice flows along the tube, S, T, which can be opened or closed by means of the stopcock R, r. This entire apparatus is covered by the lid F, G, Plate 1, Figure 2, fully opened at the top and closed at the bottom. It is made of tin covered with oil paint to ensure it against rust. To use it for an experiment, you fill it with crushed ice in the middle space and cover H, G of the inner space and the external space and the cover of F, G of the whole apparatus. Then you drain out the interior ice, thus we call the ice which is enclosed in the middle space and is covered, and which we must be careful to crush thoroughly and to press strongly into the apparatus. When it is sufficiently drained, you open the apparatus to place in it the body you wish to experiment upon, and close it again immediately. You wait until the body has completely cooled down and until the apparatus is sufficiently drained. Then weigh the water collected in the vessel P. Its weight exactly measures the heat given off by the body, for it is evident that the body is just as if it were in the center of the sphere which we have just spoken, since all of its heat is stopped by the interior ice, and since this ice is protected from any other source of heat by the ice enclosed in the lid and the exterior space. Experiments of this kind last 15, 18, or 20 hours. Sometimes to speed them up, we place well-drained ice in the inner space and cover with it the body which we wish to cool down. Figure 4 of Plate 1 shows a pail of sheet iron intended to hold the body on which we wish to experiment. It is furnished with a lid b, having a hole in the center and closed with a cork stopper pierced by the tube of a small thermometer. Figure 5 of Plate 1 represents the round bottom flask, whose stopper is pierced by the tube c, d of the little thermometer r, s. It is necessary to use flasks of this sort whether one works with acids and in general with all substances that can react in any way with metals. T, Figure 6, Plate 1, is a shallow hollow cylinder placed at the bottom of the inner space to support the round bottom flasks. It is essential in this apparatus that there be no communication between the middle space and the external space, which can be easily tested by filling the external space with water. If there is a connection between these spaces, the ice melted by the atmosphere, whose heat acts on the envelope of the external space, could pass in the middle space, and then the water runs out of the last space, which would no longer measure the heat lost by the bodies experimented on. When the temperature of the atmosphere is above zero, its heat can reach the middle space when the temperature of the atmosphere is above zero, its heat can reach the middle space only with difficulty, because it is stopped by the ice of the lid and of the exterior space. But if the exterior temperature were below zero, the atmosphere could cool down the interior ice. It is therefore essential to an experiment in an atmosphere whose temperature is not below zero. Thus, in freezing weather, you must place the apparatus in a room you have been careful to warm. It is necessary that the ice it is also necessary that the ice used not be below zero. In that case, it is necessary to crush it, spread it in very thin layers, and keep it thus for some time in a place where the temperature is above zero. The interior ice always remains a small amount of water adhering to its surface. And one might think that this water would affect the results of our experiment, but it should be noted that at the beginning of each experiment, the ice has already absorbed all the water that it can retain in this manner. So, if a small portion of ice melted by the body still adheres to the interior ice, the same quantity, or very nearly, of the water originally adhering to the surface of ice should separate it and flow into the vessel capital P, where the surface area of the interior ice changes very little during the experiment. Whatever precautions we took, we found it impossible to prevent the outside air from penetrating in the inner space. When the temperature is about 9 or 10 degrees, the air enclosed in the space has a greater specific gravity than the air outside. It flows out through the tube XY, and it is replaced by the outside air that enters through the upper parts of the apparatus, and which gives up a part of its heat to the interior ice. There is thus produced in the contrivance a flow of air that is swifter when the outside temperature is greater, and this steadily melts the interior ice. Due to a large degree, we can suppress the effect of this airflow by closing the stopcock, lowercase k, but it is much better not to experiment except when the external temperature is no greater than 3 or 4 degrees, where we have noticed that then the melting of the interior ice due to the atmosphere is imperceivable. Thus, at this temperature, we can answer for the accuracy of our experiment on the specific heats of bodies close to 1 part in 40 or even 1 part in 60 if the room temperature is only 1 to 2 degrees. We have made 2 calorimeters. Note here, since I'm going to read this note from the author. It was in the back. It was only called the machine because the word calorie wasn't defined yet. We have made 2 machines similar to that which we have described. One of them is intended for experiments in which it is not necessary to renew the interior air. The other apparatus is used in experiments which the renewal of the air is absolutely necessary, such as those on combustion and on respiration. The second apparatus only differs from the first in that which 2 lids are each pierced by 2 holes which pass 2 small tubes that provide a connection between the interior air and the atmosphere outside. By their means, we can blow atmospheric air into combustible substances. These tubes are shown in Figure 2 of Plate 1. We shall now describe the results of the chief experiments we have made with these devices. And then it says B. Since reading this memoir, we have seen a very interesting paper by Monsieur Vilk on heat, printed in Stockholm Memoirs for this year, 1781. But this learned scientist had the idea before we did of using the snow melted by bodies to measure their heat, but the difficulty of collecting the water produced by melting snow, the considerable time that bodies require to lose their heat in this fashion, in which according to our experiments can be 12 hours and even more, the heat of that the snow receives in this period of time from the atmosphere and from all other bodies that surrounded it. All these reasons forced him to abandon this method and to resort to the method of mixtures, because he did not attempt to surround the snow with snow which the bodies were supposed to melt with an external layer of snow or ice to protect it from the heat of the atmosphere. It is in this external envelope that the chief advantage of our machine consists, the first calorimeter. An advantage that made it possible for us to measure until now, such as the heat evolved in combustion and respiration. Moreover, in these experiments, ice is preferable to snow. Taking a breath break. Okay, man. Gonna get on to section 4. Almost done. Jesus. Oh. Take an hour. God damn. It's like reading a page every 10 minutes. Oh, okay. Let's see how far. Yeah, a little bit faster than that. Okay. This is for editing. This is the part to cut. Alright. I am recording. Section 4, on combustion and respiration. Until very recently, we had only vague and very imperfect ideas concerning the phenomenon of heat that is given off in combustion and in respiration. Experiment had taught us that bodies cannot burn or animals breathe without the participation of atmospheric air, but we did not know the way in which it influenced these two great processes of nature and the changes they made it undergo. The most commonly held opinion attributed to this fluid no other functions than that of cooling the blood as it passes through the lungs, and by its pressure retaining the matter of fire at the surface of combustible bodies. I feel like I missed something. The important discoveries made only a few years ago on the nature of aeriform fluids have greatly enlarged our knowledge of this subject. It results from these discoveries that only a single kind of air, known by the names of dephlogisticated air, pure air, or vital air, is fitted for combustion, respiration, and the calcination of metals. It makes up only about a fourth part of atmospheric air, and that is this portion of the air that is then absorbed, altered, or converted into fixed air by the addition of a principle that, to avoid all discussion concerning its nature, we shall call the base of fixed air. Thus, air does not act in its operations as a simple mechanical cause, but as a principle entering into new combinations. Monsieur Lavoisier, having observed these phenomena, suspected that the heat and light which are given off were due, at least in great part, to the changes which the oxygen gas undergoes. Everything having to do with combustion and respiration is explained so naturally and simply by this hypothesis that he did not hesitate to propose it, if not as a demonstrated truth, at least as a most likely conjecture worthy in every respect of the attention of scientists. This is what he did in a memoir on combustion printed in the Academy's volume for year 1777. Page 592. That would be some good reference. Mr. Crawford has offered a somewhat similar explanation in a work on the same subject published in London in 1779. These two scientists agree in regarding oxygen gas as the principal source of heat developed in combustion and respiration. There is, however, an essential difference between their views. Now, Monsieur Lavoisier thinks that the heat given off of these two phenomena is combined with the oxygen gas, and that this fluid owes its aeriform state to the expansive force of heat so combined, whereas according to Monsieur Crawford, in the oxygen and matter of heat is in its free state, it is only given off from it because the oxygen, on combining, loses a large portion of its specific heat. Mr. Crawford bases this assertion on experiments in which he finds the specific heat of oxygen 87 times greater than that of ordinary water. And if these experiments are accurate, it would be easy to show that the free heat of the oxygen more than suffices to produce all the phenomena of heat, and that even in combustions that evolve the most heat, as in that of phosphorus, the combustible amount of free heat in the oxygen should combine. But these experiments are so ticklish, it is necessary to have repeated them a great number of times before accepting them. Therefore, we shall refrain from pronouncing on their exactness until by our method we have determined the specific heats of different gases. Here we will limit ourselves to comparing the amounts of heat that are evolved in combustion and respiration with the corresponding changes in oxygen, without considering whether that heat comes from the air or from the combustible bodies and the animals that breathe. In order to determine these changes, we performed the following experiments. Capital M, plate 2, figure 7, represents a large basin filled with mercury, over which we have placed bell jar B, filled with oxygen. This gas was not perfectly pure. 19 parts of it contained 16 parts oxygen and included about 1/57th part of its volume of fixed air. Under the bell jar, we placed a small earthenware vessel, capital C, filled with fine charcoal, which we have been previously depriving of its inflammable air by strong heat, and which closely resembled that which we had used in the experiment on the heat evolved in the combustion of carbon. Above the charcoal, we placed a little tinder on which was a tiny bit of phosphorus, weighing at most 1/10 of a grain. The earthenware vessel, with all of its contents, had been very precisely weighed. Then, by drawing out the contained air, we caused by the mercury in the bell jar to rise to capital E, so that the expansion of the air caused by the combustion of the carbon would not lower the mercury too far below the level of mercury inside the basin outside, which could have allowed the air under the bell jar to escape. After this, by means of a red-hot iron that we thrust rapidly through the mercury, we ignited the phosphorus, which we set fire to the tinder, and so lit the charcoal. The combustion lasted 20 or 25 minutes, and when the charcoal was extinguished and all the air inside was cooled, the atmospheric temperature was cooled to atmospheric temperature. We made a second mark, E prime, where the mercury had risen through the decrease in volume of the air inside. Then we introduced some caustic alkali under the bell jar. All the fixed air was absorbed, and after a lapse of time sufficient for this purpose, when the mercury had ceased to rise in the bell jar, we marked a line E double prime at the level of the surface of the caustic alloy. We were careful to note the three positions E prime, and capital E double prime, the heights of the mercury above its level in the basin. Atmospheric air introduced under the bell jar by means of a glass tube lowered the mercury to the level of that outside of the basin. When we withdrew the vessel, capital C, which we dried and weighed very precisely. Its loss of weight told us the quantity of carbon consumed. Its loss of weight told us the quantity of carbon consumed. The outside temperature had varied but little in the course of the experiment, and the barometric reading was about 28 inches of mercury. To determine the volumes of air contained in the spaces capital E, B, D, and capital E prime, capital B, capital D prime, and capital E double prime, capital B, and capital D double prime were filled with water, and their respective weights give us in cubic inches the volumes of these spaces. But since the contained air was subject to different pressures because of the different heights of mercury in the bell jar, we reduced each volume of air to that which it would have occupied if it had been subject to a pressure of 28 inches of mercury. Finally, we reduced the results of our experiment to those we would have obtained if the external temperature had been 10 degrees, invoking the fact that a temperature of about 10 degrees, air expands 1/215th its volume for each 1 degree of increase in temperature. Thus, the gases whose volumes we shall give below should be thought of as having a temperature of 10 degrees and being under a pressure of 28 inches of mercury. In the preceding experiment, there were 202.35 cubic inches of oxygen. By the combustion of carbon alone, its volume was reduced to 170.59 inches, and after the absorption of fixed air caused by the caustic alkali, the volume of air remaining was not more than 73.95 inches. The weight of carbon consumed, disregarding the ash, was 17 2/10 grains. The weight of the tinder of the phosphorus together could have been half a grain. Moreover, we have found by numerous experiments that the weight of the ash formed by the charcoal is about 10 grains per ounce. Thus, we can infer that in this experiment there is very nearly 18 grains of carbon consumed, including in its ash in this figure. The oxygen which we used contained about 1/57th of its volume of fixed air, which had not been absorbed by the water over which it had remained for several months. This intimate adherence of fixed air to oxygen leads us to believe that even after the absorption of fixed air caused by the caustic alkali in our experiments, the remaining air still contained a little fixed air that we can evaluate, without appreciable error, at 1/57th of its total volume. On this assumption, to obtain the total volume of oxygen consumed by the carbon, it is necessary to take the difference between the volume of air before the combustion and the volume of air retaining after the absorption by caustic alkali. Reduce this difference by 1/57th. Likewise, on subtracting this same quantity from the volume of air absorbed by the caustic alkali, you will have the volume of fixed air produced by the combustion. Thus, you will find that an ounce of carbon burning consumes 4,037.5 cubic inches of oxygen and produces 3,221.1 cubic inches of fixed air. And if we call this volume of oxygen consumed unity, then its volume after combustion will be reduced to 0.74828. To express as weights these volumes of oxygen in fixed air, we must know the weight of a cubic inch of each of these gases. It has been found that oxygen is a little heavier than atmospheric air, approximately in the ratio of 187 to 185. The weight of atmospheric air has been very precisely determined by Monsieur Deluc. On the basis of these measurements, we find that at a temperature of 10 degrees, at a barometric pressure of 28 inches of mercury, a cubic inch of oxygen weighs 0.047317 grains. Monsieur Lavoisier has observed that at the same temperature and the same pressure, a cubic inch of fixed air weighs nearly 7/10 of a grain. According to these results, an ounce of carbon burning consumes 3.3167 ounces of oxygen and yields 3.6715 ounces of fixed air. Thus, for 10 parts of fixed air, there are about 9 parts of oxygen and 1 part of a principle contributed by the carbon, and which is the base of fixed air. But so fine a measurement requires a much greater number of experiments. We saw above that 1 ounce of carbon burning melts 6 pounds, 2 ounces of ice, where it is easy to infer that when carbon burns, the transformation of 1 ounce of oxygen can melt 29.57 ounces of ice, and thus the formation of an ounce of fixed air can melt 26.692 ounces of ice. It is with the greatest caution that we present these results concerning the amount of heat produced where carbon is burned in an ounce of oxygen gas, where we were only able to make one experiment on the heat evolve in this combustion, and although it was carried out in quite favorable circumstances, we will be really convinced of its accuracy only after having repeated it a number of times. We have already said that we cannot stress this fact too much, that it is less than the result of our experiments than the method we have used that we offer to scientists, inviting them, if this method seems to offer some advantage, to check these experiments which we observe ourselves propose to repeat with the greatest care. On burning phosphorus in the above apparatus, where the bell jar was filled with oxygen gas, we found that 45 grains of phosphorus absorbed on combustion 65.62 grains of oxygen gas. And since the product of this combustion is phosphoric acid, From this, we may conclude that when this acid is formed, about 1 in 1/2 parts, or precisely 1 in 4/9 parts, of oxygen gas combines with 1 part of phosphorus. This agrees with the result that Monsieur Lavoisier was the first to obtain in Memoirs of the Academy for the year 1777, page 69, by which subsequently Monsieur Bartholomew has confirmed by the method has confirmed by the method of chemical reactions. From this, it follows that an ounce of phosphorus on burning absorbs 65.62 and for every 45 ounces of oxygen gas. And we have seen before that it can melt 6 pounds, 4 ounces, 48 grains of ice. Therefore, 1 ounce of oxygen gas on being absorbed from the phosphorus can melt 68.634 ounces of ice. But that same amount of gas, on becoming fixed air by the combustion of carbon, can melt 29.5 ounces. When we have once we draw the pretty remark able to conclude we draw the pretty remarkable conclusion that the heat given off by oxygen gas when absorbed by the phosphorus is approximately 2 1/3 times greater than when it's changed into fixed air. The Memoirs of the Academy for the year 1777, page 587, Monsieur Lavoisier was led to a similar result by his general theory of the formation of gases and vapors. According to this theory, oxygen gas, fixed air, and in general all gases and all vapors owe their gaseous state to the large quantity of heat which is combined with them. Oxygen gas especially seems to contain it in abundance. It releases it almost entirely when it passes into the solid state, in the calcination of metals, and in the combustion of sulfur, phosphorus, etc. But a considerable part of it is retained in the form of fixed air. The absorption of oxygen gas by nitrous air provides an exception to this general theory of the reactions of oxygen. The amount of heat given off in this particular reaction is very small, and incomparably less than that developed in the absorption of a similar volume of oxygen by phosphorus. It is therefore necessary to imagine in nitric acid, and consequently in saltpeter, a large amount of combined heat, which should reappear in its entirety when this substance is detonated. And this in fact is what experiments show. On strongly heating saltpeter, Monsieur Bartholomew was able to convert into oxygen nearly all nitric acid that it contains. In addition, this able chemist has further observed that on detonating saltpeter with carbon, a large part of its acid changes into fixed air. Now, 1 ounce of saltpeter contains 3 2/3 gross of nitric acid. So, supposing that this acid contains wholly of oxygen, and that this is entirely converted into fixed air, we find, according to the preceding results on the combustion of carbon, that an ounce of saltpeter on detonating with carbon should melt 13.5 ounces of ice. Experiment gave us only 12 ounces of melted ice. But if you consider the uncertainty of the principles from which we started and the inevitable errors in the experiment, you'll see it is not possible to expect a more perfect agreement in these results. Therefore, we may perceive the phenomenon of detonation of saltpeter in this way. The oxygen contained in this substance was combined with it without the evolution of an appreciable amount of heat. Consequently, it should produce only a small degree of cold on returning to the gaseous state. During the change of state, the base of fixed air contained in the carbon takes up the oxygen and converts it into fixed air. When this occurs, there should be given off a quantity of heat nearly equal to that which is evolved in the direct combination of carbon with oxygen. The cold resulting from the change of oxygen into the gaseous state in the detonation of saltpeter produces a small difference between these quantities of heat, and this difference is equal to the amount of heat which is evolved from oxygen gas when it combines with nitric acid. We could determine it by the preceding experiment if the principles from which we started were exact, and we could find that in the combination of 1 ounce of oxygen gas to produce nitric acid, the quantity of heat that is evolved can melt 3¼ ounces of ice. These assumptions are too uncertain for us to be able in this way to determine with precision this amount of heat. However, that may be, we can conjecture with some likelihood that saltpeter owes to the heat that is combined with it its property of detonating with substances that can combine with oxygen, a property not found in other substances such as the phosphoric salts, which nevertheless contain a large amount of the same gas, but do not combine with it except with the evolution of considerable heat. To ascertain the changes which the respiration of animals produces in oxygen gas, we have filled bell jar B of the previously described apparatus with the gas, but we put in it different guinea pigs of about the same size as the one we used in our experiment on animal heat. In one of these experiments, the bell jar contained, before putting in the guinea pig, 248.01 cubic inches of oxygen gas. The animal remained in there for 1¼ hours. To introduce it under the bell jar, we made it pass through the mercury. We withdrew it in the same fashion, and after having let the air inside the bell jar cool to room temperature, its volume was somewhat diminished and reduced to 240.25 cubic inches. Finally, after having absorbed the fixed air with caustic alkali, there remained 20.56 cubic inches of air. In this experiment, there were 46.62 inches of modified gas and 37.96 inches of fixed air produced, a correction being made for the small amount of carbon dioxide contained in the oxygen gas of the bell jar. One denotes by unity the volume of modified oxygen gas. The volume reduced by respiration here will be 0.814. In the combustion of carbon, the volume of gas diminished was a ratio of 1 to 0.74828. This difference may result in part from errors in measurement, but it also depends on the cause at which we did suspect at first, and about which it is well worn to those. This difference may result in part from errors in measurement, but it also depends on a cause that we did suspect at first, and about which it is well to warn those who will want to repeat these experiments. We stabilized the bell jar in the basin. We raised the level of mercury inside, slightly above the level of the mercury outside. Now, in putting the animal under the bell jar and withdrawing it, we observed the outside air penetrated slightly into the interior, along with the body of the animal, although immersed partially in the mercury. Mercury does not adhere to the surface of the hair and the skin closely enough to prevent all contact between the outside air and that inside the bell jar. Thus, the gas appears less diminished by the respiration than it in fact is. The weight of the fixed air produced in the preceding experiment is 26.572 grains, from which it follows that the course of 10 hours the animal would have produced 212.576 grains of fixed air. At the beginning of this experiment, the animal breathing in the air an air much purer than that of the atmospheric, produced perhaps, in the same period of time, a much larger quantity of fixed air, but near the end it had difficulty breathing because the fixed air settling by its weight to the lower part of the bell jar, and probably also because the fixed air is in itself injurious to animals. We may therefore suppose, without appreciable error, the quantity of fixed air produced is the same as the animal had breathed atmospheric air, whose goodness is about the mean difference between that of the air in the lower part of the bell jar and at of the bell jar at the beginning and at the end of the experiment. We then determined directly the amount of fixed air produced by a guinea pig when it is breathing atmospheric air. To do this, we placed one of the animals under a large jar through which we passed a stream of air. The air, compressed in apparatus, very convenient for the purpose, entered the jar by a glass tube and issued from it by a second bent tube whose concave part was immersed in mercury and whose lower portion ended in a flask filled with caustic alkali. The air then passed out through the third tube, which ended in a second full flask of caustic alkali, and from there it spread into the atmosphere. The fixed air produced by the animal in the interior of the bell jar was trapped, in large measure, by the caustic alkali of the first flask, and that which escaped this reaction was absorbed by the alkali of the second flask. The increase in weight of the flasks gave us the weight of fixed air that was absorbed in them. In the course of 3 hours, the weight of the first flask increased by 63 grains, the weight of the second flask by 8 grains. Thus, the total weight of the two flasks increased by 71 grains. Assuming that this quantity of fixed air was solely due to the respiration of the animal, it would during 10 hours, have produced 236.67 grains of fixed air, which differs by about 1/9 from the result of the preceding experiment. This difference can be owing to the difference in size and strength of the two animals and the conditions of each during the experiment. If the vapors produced by respiration carried by the flow of air had been deposited in the flasks, the increase in weight of the caustic alkali would not have been given the quantity of fixed air produced by the animal. To prevent this trouble, we used a bent tube whose concave portion dipped into the mercury. The vapors from respiration condensed in the walls of this part of the tube and collected in its concavity, so that upon entering the first flask, the gas was not perceptibly laden with them. For the first part, the tube that entered the flask remained transparent. We can therefore suppose that if the weight of the flask was increased by these vapors, this increase was compensated by the evaporation of the waters of the alkali they contained. One could fear, moreover, that the part of fixed air that was combined might be due to atmospheric air. To reassure ourselves on this point, we repeated the same experiment with no guinea pigs under the jar. In this case, there was no increase in weight in the flasks. That of the second flask decreased by 4 or 5 grains, doubtless from the evaporation of water of its alkali solution. Third experiment, made on a guinea pig in oxygen, gave us 226 grains for the amount of fixed air produced in 10 hours. Upon taking the average of these experiments and a few other similar ones made on a number of guinea pigs, both in oxygen and in atmospheric air, we estimated at 224 grains the quantity of fixed air produced in 10 hours by a guinea pig, on which we experimented in one of our machines to measure its animal heat. Fun fact, since these experiments were made at a temperature of 14 or 15 degrees, it is possible that the quantity of fixed air produced in respiration may be a little less than at 0 degrees, which is the temperature inside our calorimeters, our machines. It should therefore be necessary for greater precision to determine the output of fixed air at the later temperature. This is a precaution that we propose to observe in the new experiments that we shall make on this subject. The preceding experiments, contrary to the results of Messrs. Scheele and Priestley on the changes in oxygen gas caused by animal respiration. This produces, according to these two fine scientists, very little fixed air and large amounts of vitilated air, which later is called phlogisticated air. On examining with the greatest possible care in large number of experiments the effects of respiration of birds and of guinea pigs on oxygen gas, we have always observed that the change of this gas into fixed air is the most important alteration it experiences in animal respiration. On causing guinea pigs to breathe a large amount of oxygen, the absorbing by means of caustic alkali the fixed air produced by the respiration, then in making birds breathe the residue air, then again absorbing with the caustic air the new fixed air that had been produced, we were able in this manner to convert into fixed air that had been produced. We were able in this manner to convert into fixed air a large part of the oxygen gas that we had used. That which remained had about the same goodness as it should have on the assumption that transformation of oxygen gas into fixed air is the only effect respiration produces on this gas. It therefore seems to us certain that if respiration produces other changes in the oxygen gas, they are very small, and we do not doubt that scientists who make the same experiments with large devices using mercury will be led to the same results. We saw above that the combustion of carbon in the formation of an ounce of fixed air can melt 26.692 ounces of ice. Starting from this result, we found that the formation of 224 grains of fixed air should melt 10.38 ounces. The amount of ice consequently represents the heat produced by the respiration of guinea pigs in the course of 10 hours. In the experiment on animal heat of a guinea pig, this animal came out of our apparatus with nearly the same body temperature with which it had entered. For we know that the body temperature of an animal is always very nearly the same. Without the constant renewal of its heat, all that it had in the first place would be gradually dissipated, and we would have withdrawn it cold from the interior of the calorimeter, and all the inanimate body on which we have experimented, but its vital functions constantly restored to it the heat that it communicated to its surroundings, and which, in our experiment, spread to the ice in the inner space, of which melted 13 ounces in 10 hours. This quantity of melted ice, therefore, represents approximately the heat restored in the same length of time by the vital functions of the guinea pig. Perhaps we should diminish it by 1 or 2 ounces, even more, because the animal's limbs were cooled down in the machine, although the interior of its body kept nearly the temperature. Besides, the humors evaporated by its eternal heat melted. On cooling the small quantity of ice and joined with water that flowed out of the apparatus. Besides, the humors evaporated by its eternal heat melted. On cooling, a small quantity of ice and joined with water that flowed out of the apparatus. A small quantity of ice joined with the water that flowed out the apparatus. That "and" is a mistype. If we decrease by about 2.5 ounces this quantity of ice, we will have the amount melted by the effect of the animal's respiration of the gas. Now, if you consider the errors inevitable in this experiment, the assumptions we made in our calculations, you will see that it is not possible to expect a more perfect agreement among these results. Thus, we consider the heat given off in the change of oxygen gas into fixed air by respiration as the principal cause of the preservation of animal heat, and if other causes contribute to maintain it, their effect is negligible. Respiration is therefore a combustion, a very slow one to be sure, but moreover perfectly similar to that of carbon. It takes place inside the lungs without giving off any perceptible light, because the matter of fire, once liberated, is forthwith absorbed by the moisture of these organs. The heat developed in this combustion is imparted to the blood that flows through the lungs. Once it spreads throughout the animal's body. This air that we breathe serves two purposes equally necessary to preserve life. It removes the base of fixed air whose excess would be very harmful, and the heat which this reaction gives to the lungs makes up our continual loss of heat to the atmospheric and surrounding bodies. Animal heat is pretty much the same in the different parts of the body. This effect seems to depend on the three following causes. First is the swiftness with which the blood circulates and promptly transmits even to the limbs, the heat which it receives in the lungs. The second cause is the evaporation produced in the lungs, and which lowers the temperature. Finally, the third is related to the increase observed in the specific heat of blood when, by contact with the oxygen gas, it is deprived of the base of fixed air which it contains. A part of its specific heat developed when the fixed air is formed, thus absorbed by the blood. Its temperature remains always the same, but when, as it circulates, the blood take up again the base of fixed air, its specific heat decreases and it gives off heat. And since this process takes place in all parts of the body, the heat that it produces helps to maintain the temperature of the parts of the body remote from the lungs at about the same degree as that of the lungs. Besides, however, animal heat is restored. The cause that produces the formation of fixed air is the primary one. Thus, we can lay down the following proposition. Whenever an animal is in a stable and resting state, whenever it can live for a considerable amount of time without suffering in the medium which surrounds it in general, whenever the circumstances in which it is found do not appreciably alter its blood and its bodily fluids, so that after several hours the animal system experiences no sensible change, the maintenance of its animal heat is due, at least in large measure, to the heat produced by the combustion of oxygen gas breathed by the animal with the base of fixed air furnished by the blood. The method which has led us to this result, independent of any hypothesis, and that it is the principal advantage. This method which has led us to this result is independent of any hypothesis, and that it is principal advantage. Whether the heat comes from oxygen gas or whether it comes from substances that combine with it, we cannot doubt that in the combination of oxygen gas with the base of fixed air, there is developed a considerable amount of heat. This reaction offers, with respect to the heat, phenomena absolutely similar to those afforded by many other chemical reactions, and in particular that of water with quicklime, in which renders the identity more perfect. There is, in fact, the later reaction, no light is produced. On comparing the heat given off by the combustion of carbon with the quantity of fixed air which is formed during this combustion, we have the heat developed in forming a given quantity of fixed air. If we then determine the quantity of fixed air that an animal produces in a given time, we will have the heat resulting from the effect of its respiration on the air. This is only a question of comparing this heat with that which maintains its animal heat, and which is measured by the amount of ice, and that it measures the interior one of our calorimeters. And as if we found in the preceding experiments, these two quantities of heat are very nearly the same, we can infer directly from this fact, and without any hypothesis, that the maintenance of animal heat is due in large part the change of oxygen gas into fixed air during respiration. We intend to repeat and to vary these experiments by determining the quantities of heat renewed in different kinds of animals, and by inquiring whether in all of them this quantity of heat is always proportional to the quantities of fixed air produced in respiration. Birds seem to prefer quadrupeds for this kind of experiment because they produce in the same kind of time in equal volume a larger quantity of fixed air. Thus, for example, we have observed 2 house sparrows consuming nearly as much oxygen as a guinea pig. To round out this theory of animal heat, we must explain further why it is that animals, although placed in environments differing widely in temperatures and density, always maintain nearly the same body temperature, without, however, changing into fixed air amounts of oxygen gas proportional to these differences. But the greater explanation of these phenomena is related to the greater or less evaporation of the bodily humors, and to their alterations, and to the laws according to which heat spreads to all parts of the body. Thus we shall wait before concerning ourselves with this matter until analysis, illuminated by a great number of experiments, shall have shown us the law of transmission of heat in homogeneous bodies, and passing from one body to another of a different kind. Thank you for my reading of Memoirs of Heat from Antoine Lavoisier and Pierre-Simon de Laplace, originally published 28th of June, 1783. Man, that was long. All right. Ooh, well, so glad I did that because I realized a lot more stuff. It's about the weight of the carbon dioxide and comparing that to the weight that was produced by the carbon. And I'm just really confused about this. 1 ounce of carbon on burning melts 6 pounds of ice, where we can infer that when carbon burns, the transformation of 1 ounce of oxygen can melt only 29 ounces of ice, and that the formation of an ounce of fixed air can melt 26. So it's the formation of fixed air. Because it's not just the burning itself, it's the formation. So I'm trying to understand that a little bit more. I know I just read it all, but. And if we call the volume reduced percentage, it's close. Where is that getting that 20? Where else do they get this? Chat, help me out. Not what I meant to do. Combustion of carbon, formation of an ounce of fixed air can melt that much. Okay. Trying to understand this part. An ounce of carbon on burning melts this when it's easy to infer that when carbon burns, the transformation of 1 ounce of oxygen can melt. How is it easy? Where'd you get that? Where'd you get this number from? Yeah, God, because I think I'm in section 4 is the problem. I'm in section 4. I'm in section. That's why I need section 2 and 3. I could really understand. They tried to cut in just what you needed, but they left out what I needed. What to understand it more. Should I just publish the whole thing? I guess I gotta translate it myself. Add it to the list. Do I don't know. I don't know how well this mic is working really. But I really hope that didn't get cut. Nope, not what I wanted to do. Just all right. Well, that was fun. So, I don't know why there's an echo. Alright, I am probably going to stop the stream for a sec, take a shower because I'm sweaty as hell. But thanks for the views. Um, I'll post that audiobook later. Bye.